Good morning, everyone. My name is Jay Shirisha. I'm from CSC AMLC section. Today, I'm going to describe about photonic crystal structure in social network. Introduction to photonic crystal structure. Photonic crystals are materials with a periodic variation in their refractive index, which can be engineered to control the flow of light. These remarkable structures have unique optical properties and have enabled numerous applications in advanced photonics and optoelectronics. Periodic dielectric structures. Photonic crystals are periodic dielectric structures that exhibit unique optical properties. They are composed of materials with varying refractive indices arranged in a precise repeating patterns. These periodic arrangements allows photonic crystals to control, manipulate the propagation of light, creating forbidden energy bands and enabling the confinement and guidance of photons. Photonic band gap formation. How the band gap will formation in the photons? We have three types like a periodic dielectric structure, photonic band gaps, light confinements, and periodic dielectric structure. Photonic crystals are periodic dielectric structures that exhibit unique optical properties, including the ability to control the flow of light through the careful engineering of their lattice structure. In photonic band gaps, when the periodicity of a photonic crystal matches the wavelength of light, a photonic band gap can form, preventing the propagation of light within a specific frequency range. In light confinement, photonic band gaps allow for the trapping and guiding of light, enabling the development of highly efficient optical devices and components for telecommunication and quantum computing application. Now, photonic crystal fabrication techniques. 1. Lithography and etching, self-assembly, direct laser writing, templating and infiltration. Now, step 1. Lithography and etching. Photonic crystals are often fabricated using lithographic techniques where patterns are transferred onto a substrate and then etched to create the desired periodic structure. Now step 2. Self-assembly. Colloidal self-assembly allows for the spontaneous formation of ordered photonic crystal structures, leveraging the natural tendency of small particles to organize into a periodic arrays. Now step 3. Direct laser writing. Focused laser beams can be used to directly write photonic crystal patterns into photosensitivity materials, enabling precise control over the structure's geometry and defects. Now step 4. Templating and infiltration. Templates with the predefined patterns can be filled with desired materials to create photonic crystals, followed by removal of the templates to leave the final structures. In photonic crystal fabrication technologies, lithography and etching, self-assembly, direct laser writing, templating and infiltration. In lithography etching, photonic crystals are often fabricated using lithographic techniques. In assembly, in self-assembly, colloidal self-assembly allows for the spontaneous formation. Direct laser writing, focused laser beams can be used to directly write photonic crystals patterns into photosensitive materials, enabling precise control over the structuring, geometry and defects. Optical properties of photonic crystals. Photonic crystals exhibit unique optical properties due to periodic dielectric structures. They control and manipulate the flow of light, enabling a wide range of application in optics and photonics. Key optical properties include the formation of photonic band gaps, anomalous dispersion, slow light effects, and highly efficient light matter interactions. In photoband diagram for photonic crystal slabs, radiation modes above the light lines losslessly guided modes below the light line, incomplete band gap in the guided mode spectrum. Photonic crystals, waveguides and devices. Waveguides, bending and splitting, optical filter, resonant cavities. In waveguides, photonic crystal waveguides light through intricate networks by leveraging the photonic band gaps. They can route signals with a low loss and high confinement, enabling compact and efficient optical circuits. Bending and splitting. Photonic crystal structures can sharply bend and split light beams, allow for complex on-chip optical routing. This enables the miniaturization of optical devices and integration with electrical components. Optical filters. Photonic crystals can be designed to be selectively filtered and manipulate specific wavelength of light. This makes them useful for applications like wavelength divisions, multiplexing, and optical signal processing. Resonant cavities. Photonic crystal structures can be confine light in tiny resonant cavities, leading to high Q factors and enabling low threshold lasers, sensors, and nonlinear optical devices. Photonic crystal based sensors. Photonic crystals possess unique optical properties that makes them highly attractive and sensing application. These periodic structures allow them to manipulate and control the propagation of light, enabling the detection of minute change in the environment. Photonic crystal based sensors can detect change in refractive index, strain, temperature, and the presence of specific chemicals and biochemical with high sensitivity and selectivity. Tunable photonic crystal structure. Tunability. Photonic crystals can be engineered to have tunable optical properties, allowing their functionality to be dynamically adjusted. Thermal tunning. Changing the temperature of a photonic crystal can alter its refractive index, enabling dynamic controls of the photonic band gap. Electro-optic tunning. Applying an external electric field can change the dielectric properties of photonic crystals, providing fast voltage control. Tunability. Application of photonic crystals. Optical communication, solar energy, biosensing, optical displays. Photonic crystals enables compact integrating optical devices like waveguides, lasers, and filters for the high-speed data transmission fiber optical networks. Photonic crystal structures can improve the efficiency of the solar cells by enhancing light observation and trapping. They enable advanced photovoltaic devices. Biosensing. The unique optical properties of photonic crystals makes them ideal for the developing highly sensitivity label-free biosensors to detect biological molecules and cells. Optical displays. Photonic crystals mixed with tunable optical properties enable reconfigurable energy efficient displays with vibrant colors for the screen and lighting. Conclusion. In this presentation, we have explored the fascinating world of photonic crystal structure, their unique properties, and their vast potential for various applications, from the principles of photonic band gaps formation to the cutting edge fabrication techniques. We have uncovered the remarkable capabilities of these engineered materials. cutting-edge fabricants techniques, we have uncovered the remarkable capabilities of these engineered materials. Thank you.